Hello, everyone. It's a real pleasure to be here today. My name is Félix Bussières. I'm from IDQ, and today I want to tell you about enhancing quantum communication, computing, fluorescence measurements, LIDAR, IC inspection with single photon detection. So let me start right away with our mission in the quantum sensing business unit at IDQ. We want to empower researchers and industries in advancing the frontiers of single photon science and application. That's really what gets us up in the morning. We want to build the best devices for you to take science forward. So why do we want to enhance these different fields with single photon detection? It's nice to, you probably know a lot of this, but it's nice to go over the list once again so we can see how the impact is made. So naturally here, let me just oops. I don't have the pointer. Hopefully you see my mouse properly. So naturally, there's always the ability to go beyond the classical limits and of conventional techniques like quantum key distribution and quantum computing simulation. Sometimes some situations require the highest sensitivity or faster measurements or better spatial time resolution. Here we benefit from the very low jitter of the detectors. Sometimes we can have a very good SNR, or we can actually use photon correlations to see through things. I'll be giving an example of this in my presentation. Sometimes we need to be operating in an eye-safe situation. Therefore, the signal that we're going to be measuring is going to be at the single photon level, and therefore we have to use these different techniques. So how do we achieve all of this? These enhancements, we use single photon detection techniques, time-resolved photon counting, and then also photon correlation measurements. Okay, so at IDQ, we make single photon detectors using SPADs, also SNSPDs. We combine those with the timing, control, and detection electronics. So this time controller here, and taking these two together, many different fields can be addressed. Naturally, quantum physics, the main topic of this very nice conference. You know it very well. I'll be talking about this a bit, but also optical communication, many applications in life science, material science, OTDR, LIDAR, security surveillance, oil and gas. I'll be giving in my talk some examples of applications in these different fields. But before getting there, let me talk about the technology a little bit. SPADs are reverse biased avalanche photodiodes that can be operated in the so-called gated mode, where the voltage is momentarily taken from this point here to this value there, just around the breakdown voltage. And if a photon comes at this time, a macroscopic current can be measured. So it goes here. And then by bringing the current back down to this point, we quench the avalanche. And this mode is synchronous in the sense that we have to know when the photon comes in. This can be achieved using our latest single photon detector, the ID small form factor, very, very nice, very handy, and very good specs. And in that case, it generates the gates, the gating inside, but you can tell it when to gate using the output of the time controller. And then the output can be going into the inputs of the time controller for detecting, for observing and doing processing with several single photon detectors. Now the cube doesn't need to be operating in the gated way only. It can also operate in a free running mode. And in that situation, the voltage is maintained here until there's a detection. And then the circuitry senses that there's a photon that was detected, and it brings the voltage here, waits a bit, and then rebiases it to have it ready for a next detection. And this mode is asynchronous, also called free running mode. And in that case, we don't need to gate it. We only need to record the output of the detector there. We have a line of detectors. If you want to have more details, just come to our booth or contact us. We'll be happy to tell you more about it. Now, I do want to talk about SNSPDs a bit more, because SNSPDs are the kind of detector that offer today the best performance in all across the board. So I want to talk about this because we do make those. So the operation principle is that we have a nanowire. It's more like a nanostrip we cool it down to below the critical temperature and to below the critical current. And when a photon comes in, it's going to break about 1,000 Cooper pairs. It creates this region of weakened superconductivity where interaction with the current can lead to a full resistive region here. And if we put that device into a biasing circuit such that initially all the current goes in here, because this switching resistance which models this process here is initially in the zero resistance branch. Well, when there's a detection, we switch from zero resistance to about 1 kilo-ohm, and the current leaves that branch and goes into this amplifier there. This gives rise to this very sharp rising edge, and then the device cools down, the current goes back into the detector, which gives rise to this lower decaying falling edge here. So this is all completely passive. It's an asynchronous detector, and at IDQ we make all of our detectors ourselves entirely in Switzerland. So what do you get with SNSPDs? You get this pre-running operation, so there's no need for synchronization, but you also get really high efficiencies, up to 95% in some cases, really no noise, less than 1 count per second or less than 100 counts per second, depending on the wavelength, very low jitter, a few tenths of picoseconds, and then very short recovery times so that detection rates in the tens of megahertz can be obtained. We put the detectors in this cryogenic system here, cooling down to 0.8 Kelvin. Every detector has its own cryogenic amplifier, which helps with jitter, and the detectors are sitting about here at 0.8 Kelvin. There's an upside with SNSPDs. The efficiency is really broadband, high efficiency over hundreds of nanometers. I'll be showing a bit more of that. And then you can have a lot of channels in one detector, 16 in that case. That becomes a very cost-effective solution if you need a lot of detectors. We operate our detectors in a true latch-free operation. There's no latching whatsoever, ever. And if you have used SNSPDs in the past, maybe you know that this can be very problematic. Well, we don't have this problem, so just contact us if you want to know more about that. And we can also do photon number resolution, a bit more on this in coming slides. So typical spec, not typical, but some specs at the 1550, the efficiency will be between 80 to 95%. Here I have an example of 95%, one of the best detectors that we have. And we activate this efficiency here and dark count rate with the bias voltage, and the switching current is about here. The dark count rate for this wavelength will be between 10 to 100 count per second at the maximum efficiency. And this is black body photon dominated. They're very broadband, so we get pretty much the same specs at 1310 nanometers. Another example at 1064, also a very high efficiency, and typically it's between 80 to 95 at the optimal polarization. At this wavelength, we have lower dark counts, less than 10 counts per second. And similarly at 780, 950 range, we can get dark count rates below 1 count per second. So really high efficiency, really dark count rates, so really exceptional devices with regards to that. In terms of broadband, I give here 3 examples. This is a detector that's optimized for high efficiency in the 1310 to 1550 region. So you see it's very, very broadband. It also doesn't decrease really fast on that side. So they do detect at up to 2 microns, a bit more. So if you want to know more about this, please contact us. This is a broadband detector optimized for 1060 nanometers, very high efficiency for that specific detector there, and high efficiency over hundreds of nanometers. This is the most broadband detector that we have. And here's another one at 850 nanometer. Here again, broadband is obvious. So if you want to do something like single photon spectroscopy, fluorescence, and you want to get high efficiency over a large range, then these detectors are excellent for that. We also do PNR, photon number resolution, and we do this by having an active area divided into several different sections that we connect together in parallel, and we read out with one coaxial line, and we make sure we do it in a way that we don't get latching from these detectors. And then if one section clicks, then we're going to get this signal here on the scope. If 2 sections clicks, you get this one. 3 section, 4 section, and so on. And we can get several sections clicking simultaneously. Now, these detectors have a very pristine PNR resolution. You can see it from the fact that these don't overlap at all. But also, once one section clicks, the other ones are still available for another detection. And so in a way, it's virtually a zero dead time detector, and they are going to intrinsically count really fast, up to 100 megahertz in some cases. And then this is intrinsically built in. The DCR is not changing with these devices, which is really nice. Here's another trace. This is a scope trace where we accumulated many different amplitudes, up to 8. This is 1 photon, and this is 8 photon click. And you see that the different peaks really barely overlap, which demonstrates the high quality of the PNR resolution of these kinds of detectors. Okay, so again, our mission is to empower researchers and industries in advancing the frontiers of single photon science and application. So let me jump in some applications where we do enhance them using our techniques. So here's an example, quantum key distribution over very, very long distances. This is an experiment that was done at the University of Geneva. In 2018, they wanted to really extend towards long distances in optical fiber, the distance over which QKD can be done. And for this required the development of and the use of SNSPDs. And the goal there was to take an SNSPD with about 80% efficiency, really low dark count to start with, 10 hertz, and then apply some extra filtering to get rid of the black body photons that are at the origin of this dark count rate, and decrease it to 1/10 of a count per second. So a dramatic decrease in the dark count rate, but still a very, very good efficiency. And this large efficiency to detection rate, to dark count ratio, was the necessary key in order to make sure that the very few photons that make it all the way to the end of the optical fiber, 420 kilometers, could be detected and could still generate a positive key rate. So that was done, and it's a very good example of how the technology can push, the detection technology can push the experiment. So the next step with this system was to operate at high rates at lower distances. This is an example where the detectors were, the SNSPDs that were used are these parallelly connected detectors, which count faster. And then by using 4 of them, over 50 kilometers of optical fiber, the raw key rate, or actually the secret key rate, was close to 10 megabits per second. So over this distance is an excellent result. Over shorter distances, less attenuation, a bit more than 10 megabits per second were obtained. So that again, it was possible thanks to the use of the right kind of detector in that experiment. So another experiment also done at the University of Geneva, it's the characterization of integrated single photon entanglement sources based on silicon nitride microring resonators. These can be integrated, and then the idea there was really to demonstrate that they can be good sources of entangled photons. So a pump is pumping that, and through spontaneous four-wave mixing, a pair is created with time-band entanglement or energy time entanglement, and then the combination of the ID 281 technology and the time controller was used to reveal a couple of things, among others, the thermal character of an unheralded single photon here. So it's thermal, therefore the zero time autocorrelation second order should be equal to 2, and that's what we see there, almost at 2. And you see this function is very narrow in time, so you need a very good system jitter, which was obtained by using the time controller and the ID 281 SNSPD detectors. To reveal the entanglement, the focus was, this was obtained by having large efficiency and low noise to get these pristine entanglement fringes. So for simulation and computing, this is a natural application of SNSPDs because you have these high efficiency, low noise, large number of channels, low jitter, and naturally this is a good end use for these systems. So by the way, the detectors can be put in a standalone cryostat or also in a rack solution for mobility if that's something that is useful for you. Here's a more industrial application outside of the quantum optics lab. So the European Space Agency has its launcher program, the Ariane launcher, and they're going to launch very soon, and it's maiden flight, the next generation Ariane 6 launcher. And one of the things they introduced there is optopyrotechnics. The goal of this is to fire up the charges that lead to the separation of the different parts in the launching sequence. First, the boosters, and then the different stages here, and then the fairing. And then this is done by sending an optical pulse or several optical pulses through a maze of optical fiber inside the launcher. And these detonate the charges that lead to the separation of the different stages. So this is done, and then so they needed a way to guarantee the integrity of this optical fiber maze, that everything was connected properly, no problem. And therefore, they needed an extreme OTDR. So the requirements were really demanding, very good spatial resolution, short measurement times, ability to measure the loss. And this was done in a large core optical fiber. So very demanding. And actually, so we spoke with them, and then we realized and showed to them that the only way to achieve their requirements was by using SNSPDs that have high detection rates, low jitter, high efficiency, and so on. So we made systems for them. They're used at different locations around the world in the preparation of the different parts of the launcher and also on the launch site to verify the strain of these different chains of optical fibers. And it's very nice to see that this technology is used not only in quantum optics lab, but also in a very demanding industrial application. All right, here's another very fascinating application of these technologies. So friends and collaborators at the DLR, I've been developing for a few years an IC inspection technique where, by looking at the very faint light that is emitted by transistors when electrical signals go through them, you can actually see if the device or the layout of the IC is correct, if there's any defect, and so on. And you can see the device come live by looking at the light emitted in time by this device. So they have made a setup where they can look at this light and they time correlate the electrical signal with respect to the detections. And then they have made this very nice video where we see this come alive. So they've looked at this device under test, a CPLD, and then there's these different logic elements. And then by looking at it with a still camera, CCD, you can produce a still image. Okay, you see the fluorescence there. But then as you look at it with a single photon detection and the time correlation techniques, as the electrical signal travels through the device, you can time correlate the detection at which you see photons with that, and you see the device come alive. So different parts of the circuitry lights up, and you end up making sure that everything is all right, and you see it go forward. And you see the time scale here is really, really short. So this is possible thanks to the very good time resolution of the single photon detectors there. All right, let me go through another application, fluorescence measurement, and more precisely, singlet oxygen. So singlet oxygen is an excited state of oxygen. It's used in photodynamics therapy. So if you want to observe the fluorescence of singlet oxygen, you need to shine it with a laser, 532 nanometer in that case, and you look at the fluorescence, you couple that into an optical fiber, you have this free running detector there, and time correlating everything in a time controller, you can reconstruct this fluorescence in time, and you can learn about the environment of the singlet oxygen. So here are some examples of that. So when we look at singlet oxygen in rose Bengal, a dye, you're going to get this curve here. As you see, you excite it, and then the fluorescence builds up for some time and then starts going down. And if you look at this, well, this shape here really depends on, well, it shows the presence of this singlet oxygen, but it also tells you about its surroundings. For instance, if you add to the mixture sodium halide, this will completely inhibit the fluorescence, and you don't see it. You see only the black peak here. So something that allows you to really see what's going on. Here's another example taken from this paper here, where advanced techniques that can be implemented, for instance, with a time controller, can be used to reproduce directly the very nice exponentially decaying luminescence signal that you have there. Okay, here's another example, LIDAR. So LIDAR is used in the automotive sector. It's used for perimeter surveillance and security. And the idea is to shine a light beam, and then a hard target will be hit. And then by looking at the time of flight, you see where this target is located. So you can do a prototype using the ID 900 to the time controller to trigger the pulse laser, and light comes out. And then this can go onto an array of SPADs. And an array will be useful because you can play tricks with correlations there. So if you look at the output of the SPAD array, by the way, this could also be a PNR SNSPD. It would do the same effect in the end. You can look at what's coming out of that, and then you can actually try to analyze properly what's going on there. So more precisely, the interesting thing is the following: there's always spurious light coming out of or getting into the system, and this spurious light, background light, is randomly distributed in time. It doesn't bunch. However, the photons coming from the hard target, they will bunch together. And if you look at the sum of all of these, they're going to produce a very large peak. And if you put a threshold, you can discriminate this large peak from the background light, which will tremendously improve the SNR. So at IDQ, we did a prototype of that by using an OEM version of the cube. And then the time controller, here's what we built. And we've been testing it in fog, and that's an interesting thing. So the target there is partly hidden by the fog, but nevertheless, we see the clear signal, and we can get rid through this SNR trick of the diffused reflection of the fog. So by playing tricks with these see-through correlation, you can actually enhance your signal-to-noise ratio. So in partnership with SK Telecom, we put everything into a small device here, and then this was demoed at CES 2019 and 2020. Okay, so I'm getting at the end of my presentation. I told you about enhancing several applications with single photon detection techniques and single photon detectors. So I told you why we want to do this. Hopefully, I was able to give you examples that are interesting to you. If you want to discuss them more, please feel free to contact us. How do we achieve all of this? We achieve it with the right technology, and we strive to offer you best performance, best user experience, and that allows you to do the best science that you have to do. You don't concentrate on the apparatus, but you really concentrate on science, and hopefully we collectively bring it forward. So check our website. We have a bunch of webinars on several topics that I discussed here today. So if you want to learn more, don't hesitate to go there. You can watch them. And with this, I want to thank, on behalf of IDQ, I want to thank all of our collaborators, and I want to thank you all for your attention. And I'll be taking questions. Okay, so there's a question by Marian. How are you sure that there was only one photon and not several of them? I guess the question is the question regarding the SNSPDs. I will assume it's regarding the SNSPDs. So to be sure, let me just bring back the slide. Here, let me. Okay. All right. So any PNR detector is never able to confirm that there was one and only one, because it's always possible that the photon was lost somewhere. But it can know that if we had 2 clicks, then 2 photons were detected, and perhaps another one was detected on the same the same pixel, and there's no way to distinguish about that. But then if you look at the photon statistics, you can reconstruct the property for a null event or another event leading to that, and you can actually understand, at least with a very high probability, that you had the right event that you were looking at. So hopefully I answered the question properly. Okay, so if there is no more question, I thank you all. Thank to the organizers for this nice conference, and don't hesitate to contact us at IDQ if you have if you want to talk about any of this. Thank you very much.